Okay, now I'm going to import the mesh we created into Fluent. So I start Fluent. Notice that you have to use the 3D version of the Fluent. Then File, Read, Mesh, then find the mesh file. The ICEM created a mesh file, the ANSYS Fluent mesh file with a file extension of .msh. It's not the latest file extension used in Fluent. So here you want to change that to .msh here. Then you find your mesh file. Okay, you read the mesh file into Fluent. Okay, then you want to check the mesh quality. Make sure you do not see any error messages here. You can display this mesh. Okay. Then model. In fact, there's pretty much nothing we want to change here. Maybe one thing you have to consider here is the viscous model. If the boundary layer over the rocket surface is turbulent, you have to use a turbulent model here, and by default the turbulent model adopted is the SST K omega model, which probably is the best you can use. But if the boundary layer is laminar, you want to use laminar model here. Okay. Whether it is laminar or turbulent depends on Reynolds number. Basically, you will want to do a simple calculation of the Reynolds number, which is the rocket speed then multiplied by the rocket diameter then divided by the kinematic viscosity of air. If you find this Reynolds number is higher than a certain critical Reynolds number, which typically is 500,000, then the flow becomes turbulent, otherwise it is laminar. By default, the material that will be used in any fluid region or fluid zone is air. So you don't need to change that. You can see here we have two fluid zones corresponding to different mesh types, right? In this fluid zone we have structural mesh. In fluid 2 zone we have unstructured mesh, but in fact they are okay. Anyways, we use air as the material in both zones because they both are recognized as fluid zones. Boundary conditions, you can see we have one inlet here. Okay, air flows into this domain through this surface. In fact, we also define the side surface as inlet, and we have one outlet here, right? We don't need to worry about those internal faces. Okay. We also have one solid, in fact two solid wall surfaces, which are the head and body of the rocket. Okay, we first set up the boundary condition for the inlet. Here, by default, it's a velocity inlet condition, which is very good. Okay, it's correct. Fluent basically identifies this inlet conditions, inlet boundary. So it directly gives it, assigns it with a velocity inlet condition. So double click that. Then you can give the velocity of the air that enters this domain. Okay, so here notice that we attach the reference frame to the rocket. So the rocket basically is stationary in this reference frame, but air flows toward the rocket with the rocket speed. Here, because the side surface is also considered as an inlet, so it's probably the best to specify the components of the velocity. Okay, that is the x, y, z components of the velocity. So both x and z components will be 0, but the y component is not 0, but negative, I don't know how many meters per second. How about 20 meters per second? I don't know. Okay, so apply and close. So this is the inlet condition. Outlet condition by default is set to pressure outlet. So you only need to specify the pressure here, which the gauge pressure is 0, and that is good enough. Okay, so you don't need to change that. The wall condition is, very simple, no slip condition, which means the air sticks to the rocket surface. Okay, the air velocity becomes 0 at the surface of the rocket. So again, there's nothing you want to change. Here you can change the surface roughness. Say the roughness height. Here I do not know the surface roughness height, so I still assume the surface is smooth. Okay. Okay. So basically, there's nothing you want. I mean, you need to set in Fluent. Not nothing, but very few things. Only a few things you need to set up in Fluent. Then monitors residue. Here you want to change the convergence criteria for the continuity equation to like a smaller number, okay, like 1e -6. Just make sure that the code is not going to stop before it really converges. So I use a very small criterion to keep the code iterating. Next, okay, then here, okay, if you want to know for example, the drag force over a specific part of the rocket surface, for example, the flap, okay, on your real rocket, or here on my mock rocket, if you want to know, for example, the drag on the head portion of the surface, you can do that. Okay, you can report, I believe it is here. Okay, you can report see probably not here. Okay, okay. Anyways, that can be done. Okay, we can do it later. Okay, initialize. We have to initialize all the variables we are going to use in our simulation, like velocity, u, v, w, right? Those velocity components and pressure and those things. You can use hybrid or standard initialization. I will use standard. I will use those variable values at the inlet as the initial values everywhere. Okay, so initialize. Okay, now every variable has an initial value. Then you can begin iteration, right? When you iterate through equations, you should always make sure that the variables involved have some values already in them, so that you can do calculations based on those initial values. Okay, then I can run my calculation. Number of iterations, let's first run like 100 iterations. Calculate. Say it's very simple to use, right? It's not rocket science. Okay, you can see it takes pretty long to do the calculation. In fact, it will take much longer to really converge, okay, to have a converged solution. But not super long, okay. For your case, probably it will converge in a few minutes. Definitely less than, say, 10 minutes, okay. That's my experience. Of course, if you keep refining your mesh, okay, if you have, say, several million mesh cells, or sometimes even, say, 10 million mesh cells, it will take longer to converge. Okay, I'm not going to wait until it converges. Okay, how do you know it converges? Basically, you see here the so-called residue of each equation keeps decreasing, right? The residue, roughly speaking, is the difference between the left side of your equation and the right side of your equation. So because Fluent is using iterative methods to solve those partial differential equations like Navier-Stokes equations, so the left side and the right side of those equations are not exactly equal to each other. Okay, it is trying to bring down the difference between the left side and right side, but the difference is typically not exactly zero. Okay, that difference is the residue. It should keep decreasing with iterations. So you should eventually observe that such residues level off. Okay, they stop changing. Then your iterations converge. So I'm not going to wait until convergence. Okay, I stop here. Then I want to, for example, I want to know, say how much drag force I have over the head of the rocket. What I can do is, I believe it's here, reports, forces. How good is that? Forces, head. Okay, I want the force in the y direction, because if the force in the x direction, it should be 0, right? It's not exactly 0. It's 0.31 Newton. So how about the y force? Okay, the y force is negative 17.8 newtons. It is negative simply means that the force is pointing downward. Okay, the upward is a positive y direction. The drag force obviously is pointing downward, right? So this is only the force upon the head. If you also calculate the force upon the body, it's much higher, right? It's much higher force. It says it also can calculate the center of pressure, which I doubt. Okay, if I calculate the center of pressure, value is 0. Is that correct? 0y. Really? Okay, that's good. It can give us. No, I really don't think so. That's interesting. Set coordinate x equals 0. Then the center pressure is at 11.6 some meters high. I do not quite understand this. Okay, if 0 is 0, then y is still 11 point something. Probably that makes some sense, but anyways, I do not quite understand how the center pressure works. In my opinion, it seems that the center pressure should be calculated based on some angle of attack, non-zero angle of attack results, but anyways, I guess my feeling is that this center pressure in fact is basically the point of the acting point of this drag force. Okay, it's probably just calculate the relative magnitudes of the drag force on the head and on the body, and then figure out the acting point of this overall drag force. This is, I'm not sure if this is the real center pressure you want to know. Okay, maybe it is, maybe it's not, because center pressure probably is more about the lift force, so that will be greatly affected by the angle of attack. But anyways, this is the general procedure of using fluent to find the forces.